Where were we last time? Can somebody tell what we have done till now? The stress matrix. So we have seen that in order to represent the state of stress, you require three traction vectors, and they are represented in the form of matrix, where each row represents the traction vector in x, y, z plane, and the columns represent the components in x, y, z direction. Now, today we will prove that these three components are sufficient to determine stresses in any arbitrary plane. That is, from the stress matrix, that is the traction vectors on the x, y, z planes, we can calculate the traction vector on any arbitrary plane which is having any arbitrary direction. So that is what we will prove today, and also we solve numerical problem based on that. Before that, just a few preliminaries. So as I announced in the last lecture, the stress tensor I given one small video about 8 minutes. So you can go through this video, and after this video, you shall solve one quiz. So based on that video, you have to answer 4 questions. So these 4 questions, you can have multiple number of attempts. So there is nothing, and after every attempt, you will come to know what is right answer, what is wrong answer. So it is simply just practicing this particular quiz, but it will just make your concept. What you are looking at the video, you can relate to these questions. So your learning will become easier. And this you have to upload in the sense, when you submit it, it will be stored as an assignment. It comes under the assignment section. Okay, now we will come to what is known as Cauchy's equation. Cauchy's equations or Cauchy's theorem, it gives us the equations by which we can convert the stress matrix or the numbers of the stress matrix into stresses in any arbitrarily oriented plane. So what you see here is a tetrahedron which is drawn along the coordinate axis. So this is x-axis, vertically is y-axis, and the last one is the z-axis. What you see here is a tetrahedron. That means it has got all triangular faces. So the triangular face which is formed in the xy plane is the x plane on which the stresses are given. On other plane, sorry, this is not x plane, this is z plane. This plane is the x plane and this plane is the y plane. And on each of the plane, we have the traction vector defined. So this figure may be complex, so we'll see in 3 dimension what we are talking here about. So what we are talking here about is a tetrahedron, what you can see here. So it has got all triangular faces. Out of all planes, the plane what you see here, one which the arrow is drawn, is the unknown plane on which you want to calculate the traction vector, and the other planes are the planes which are parallel to x-axis, y-axis or z-axis, or normal to x-axis, y-axis, z-axis. So in this case, this red is a x-axis. This particular triangle, what you see is the normal to this plane is along x-axis. So this is x plane, and on this plane you have the traction vector defined. So what you see are the components of the traction vector. The normal component would be sigma x, and the others will be tau xy and tau xz. So those are the other two components. Similarly, you will see the other face. So this particular face is the normal to this particular face is perpendicular to y-axis. So this plane, again you have got the second traction vector. This traction vector has got certain normal component and two shear components. And the last face is the bottom face, which is shown here. So on this plane, again you have got the one normal component and three shear components. What we are trying to do here is some arbitrary plane. So these three triangles are not equal, they can be of unequal sizes, and the three vertices, those are formed after these triangles, they constitute a plane. So this plane can be oriented anywhere in the space. So you have this x-axis, y-axis, z-axis, and what plane shown here is an inclined plane. So that is what is being shown here, and normal to that plane is n bar. So n bar could be anything, and depending on the orientation of n bar, the traction vector on this plane will be different. So what we see here is this magenta vector is n bar. So this particular vector is perpendicular to this plane. So if you orient the plane in this direction, you can see that this is the orientation of plane, and in space this magenta vector is the n bar vector where it is perpendicular to. The traction vector which is unknown on this plane is Tn bar. So Tn bar is the traction vector which we want to find out. What is known to us is on x plane, y plane, z plane, those are the three triangular faces. So this is x plane, the other one is y plane and z plane. So once you know the traction vector on the three planes, you know the stress state at that particular point. Based on that, you should be able to calculate Tn bar. So once, if you can prove that using these three numbers, you can get Tn bar, and since this n bar can be any vector, it proves that using these three numbers you can calculate stress state at any of the 3 points, any of the arbitrary plane that is oriented in the space. And that is what the Cauchy's equation or Cauchy's theorem states. So we'll derive the equations of how do you obtain the components of this Tn bar in x direction, y direction and z direction. So is it clear what we are doing here? So we have taken some point in the body. So this particular point that we are talking about is some point in the body which is having some support, some loading and so on. About this particular point, we have drawn the xyz coordinate, and what tetrahedron you see here is constituted at this point. So instead of creating that cuboid, we are constructing this particular triangular tetrahedron because we get, you can imagine it as a diagonal plane of a regular brick. And this particular arbitrary plane is the plane where we want to know what are the traction vectors. Okay, so the procedure for this is based on the simple equilibrium equation. So what you do here is we'll consider the summation of forces in x direction equal to 0, summation of forces in y direction equal to 0, and summation of forces in z direction equal to 0. So these three equilibrium equations will lead us to the three separate equations which are called as Cauchy's equations. So here we will see what this sigma fx equal to 0 leads us to. So that will lead us to first Cauchy's equation, and the remaining two can be similarly developed. Okay, so let's see what forces are acting along x direction. Okay, so this particular vector Tn bar, so remember that red direction is the x direction. So this is the x direction. On this arbitrary plane which has got normal vector as n bar, you are having the component of this Tn bar along x axis as Tn x bar. So this is the component, Cartesian component of this traction vector along the x axis. So if you note the traction vector along x axis, can you tell how do you calculate force from traction vector? What is the definition of traction? So traction is a ratio. So it is a ratio of what by what? Force upon area. It is just a force. It is just like what you strength of material learned about stress. The only difference between stress and traction is that stress is a tensor. That means it requires an additional information, whereas the stress vector or traction vector is a vector. So it has only magnitude and direction. So magnitude is given by the force divided by area, and the direction is given by whatever direction you are talking here. So here Tnx is oriented along x direction and its magnitude is given by Tnx. So if the Tnx is the magnitude, and let's say area of this particular face is A, so I will call the area of this face equal to A. So because of the x component, so here we are talking about this Tnx bar. So what will be the force in the x direction because of Tnx? So this traction vector is acting on a triangular face whose area is equal to A. The magnitude of traction is Tnx. So what will be the force in x direction? The traction into the area on which it is acting. So this particular equation leads us to, so Tnx is the component in the x direction multiplied by area. So that is the force in x direction. And you have to add up all forces on all the faces in x direction and sum them up equal to 0. So let's now move to the x face. So x face is this face. So this is the x axis and this is the triangular face whose normal is along x direction is the x face. So this is the face that we are talking about. Now on this face there are three components of traction vector. There is one normal component and there are two shear components. So out of these three components, which component is along x direction? Sigma x. So normal component is along the x direction. So sigma x is only contributing to the x direction forces. The remaining, what is this blue? Can somebody tell what is the designation of blue? So this is z direction. Blue is the z direction. So take tau acting on x plane in z direction. So that is tau x z. But this is acting in the z direction, so it will not contribute to our equation sigma fx equal to 0. So we have to only consider sigma x and area of this particular triangle. So area of this particular triangle, let's call it as Ax. Later on we'll find out how to relate Ax and A. So I am calling this particular face sigma x. As having area Ax. So note that the forces are drawn in a particular fashion. I am assuming that this traction is pulling this triangle towards the right. So in order to have an equilibrium, you require the sigma x in the opposite direction. So that is why sigma x is shown in this particular direction. Okay, so in this particular equation, we have Tnx into A. So that is the force which is acting in positive x direction. Now on this phase, is this force acting in positive direction or negative direction? This is positive x direction. It is opposite to what was acting on the plane. So this is negative. So it is, and what is the value of this force? It is sigma x, that is the traction, multiplied by area of that particular triangle. So that is A. Now let's move to the y phase. So y phase is the green phase. I'm not able to slide it. Okay, so this is the phase that we are talking about, and we are dealing with the x direction forces. So on this phase, we have to determine what is the force acting along the x direction. So this is the phase. So there is a normal component on this phase. So what will be this component called as? That will be sigma y. It is on y phase acting in the y direction. So this is sigma yy or sigma y. And there are two shear stress components. Out of this two shear stress component, this component in our, it is written here as tau xy. What would be in our conventional nomenclature? It is acting on y plane in the x direction. So it will be tau yx. It is written here as tau xy. So y, we can write tau yx equal to tau xy. So that is some property of this shear stresses. It is a equality of cross stress. Very good. So that is the reason that xy are written here as tau xy. So this is the component which only contributes to the forces in x direction. So let's call this particular area as Ay. So Ay multiplied by tau xy will give you force in the x direction. Contribution from the y plane. So we will have minus y minus, because here all the forces, or the, if you notice, all the forces are drawn opposite to the force which is acting on the arbitrary plane. So that is why it is negative. That is why I have written here negative. So it is minus tau xy multiplied by Ay, where Ay is the area of this particular triangular face. And finally, the last phase. So now we are talking about the Z phase, so which is the bottom phase of this tetrahedron. So we have on this phase, what is this blue component would be called as? It is sigma z, and there are two components, out of which the component which will be in x direction is shown here in red. So what will you designate this stress as? It is tau zx. So that is what is written. I have written here in the xz just to maintain. So in this course we will be writing in the sorted by the coordinates. So x, y, z. So yz will be yz, zy will be again yz, and xz, zx will be written as xz. So this is the xz component which is opposing to this Tnx component. So it would be minus tau xz multiplied by Az. So that is the forces which are coming because of the internal resistance. So all these traction vectors are the material is resisting whatever external forces are acting on that particular body, and that resistance is given by this, the stress traction vectors which are given here. In addition to that, in most of the engineering problems, you will have either the self weight or the body is accelerating. In that case, there will be some inertia forces which will be acting on the body. So those inertia forces, they are called as body forces. So just like traction is force per unit area, body forces are force per unit volume. So they are mentioned in terms of per unit volume type of components. The most common type of body force is the weight of the body. So if this particular triangle has got some weight, and let's say the gravity direction is x direction, so whatever is the density multiplied by g multiplied by the volume of this particular tetrahedron will give us the force which is acting in the x direction. That is, let's say this x is the gravity direction. In that case, g is the acceleration in the gravity direction. So mass into g, m into g will be the body force magnitude, and that magnitude can be written as, instead of mass, you can write rho multiplied by density, rho multiplied by volume. So volume of this tetrahedron multiplied by the body force magnitude. So body force in this particular derivation, we will be calling them as with the component gamma. So it is in the x direction it is gamma x, y direction it is gamma y, z direction it is gamma z. And the unit of this is Newton per meter cube. So they are force per unit volume type of components. Now this tetrahedron, so suppose this particular body has got certain acceleration in x direction, y direction and z direction. So because of that acceleration, you will get mass into acceleration as the what you learned in engineering mechanics as a D'Alembert force, which converts the accelerating body into a static problem. So these are nothing but mass into acceleration. The density into acceleration. So that is what this particular component gives you. So this particular tetrahedron, let's say gamma x is the body force magnitude in the x direction, or simply the acceleration in the x direction. The component, because of the body force in the x direction, would be given as gamma x. So this will be plus. I am assuming it is accelerated, gamma x is in positive x direction. So it will be gamma x multiplied by volume of this particular body. The volume of this tetrahedron is what is to be included. Other than this particular tetrahedron is not subjected to any other type of force. So this would be equal to 0. So that is the equation that we have got. Now we have to simplify this particular equation in order to proceed further. Do you have any question at this particular point? So what we have done, we have taken this tetrahedron, summed up all the forces which are acting on this particular tetrahedron. So this is a force which is acting on the arbitrary plane in the x direction. This is the force acting on the x plane, force acting on y plane, force acting on z plane. And this is the volumetric force, what we call as a body force, which acts in the x direction. And this body force arises because the body may be accelerating in that particular direction. Or simply there will be some magnetic pull, or there can be some gravitational pull in the x direction. Okay, so that is the thing. Now we have to simplify this particular equation. Okay, so now there are some coordinate geometry relationships that we'll be using in order to resolve this particular x, ay, az components. So this arbitrary plane has got normal vector which is given as n bar. So n bar can be written as nx I bar plus ny j bar plus nz a bar. And this is a unit vector. What do you mean by unit vector? Anybody knows? Unit vector, what does unit indicates? a unit, its magnitude is equal to unity. It is having unit magnitude. And in that case, this nx, ny, and nz, they are called as direction cosines. So nx is cos of alpha, ny is cos of beta, and nz is cos of, I'm just not using gamma because it will contradict with this. So where alpha, beta, gamma are the angles which this vector is making with respect to x, y, z plane. So if you have x, y, z, and this is n bar vector, the angle between n bar and x axis is alpha between y and n bar. So we are talking about space angle, not the projected angle. This is beta and this is delta. So if you take these three angles, means how to determine this nx, ny, nz, I am just giving here, not related to solid mechanics, related to the vector algebra, but just to refresh your knowledge. So this is how nx, ny, nz will be determined. They are called as the direction cosines because their definition includes cosine of the angle. Okay, so that is just a refresher as to how the vector is defined. So this particular plane will have certain a normal whose direction cosines are given by these particular numbers. Once we know this number, there is a relation in the three-dimensional coordinate geometry by which for a tetrahedron, so tetrahedron you have got an area which is oriented, the normal is oriented in n bar direction. In that case, the ax, ay and nz, they are related to this a in the following manner. So for tetrahedron, ax is given as nx times a, ay is given as ny times a, and az is given as nz times b. So whatever area of this particular triangle, if you project this triangle along x-axis, along the x-axis, that's right. If you project here, that is on the yz plane, you get this particular area. So this particular area x is projection of this space plane onto x-axis, and it can be proved that this x is equal to the direction cosine in the x direction multiplied by area of that triangle. Similarly, ay equal to direction cosine in y direction multiplied by a, and az is given in this particular manner. So that is one equation which we will substitute in this equation. And the volume of this tetrahedron is given as 1/3 a multiplied by h. So that is another geometric relationship where h is the distance between the vertex. So if you calculate the height of this tetrahedron, so this is h, which is from the origin of this particular tetrahedron. If you drop a normal onto this n bar plane, whatever is the height of this particular triangle, height of this particular projected vector, that I am calling as h. So the volume of this particular tetrahedron can be given in terms of 1/3 a into h. So it is something similar to the height of triangle, half ah. So instead of half ah, the volume is given as half, or rather triangle ke liye half base into height. For the volume, it is half area, base area multiplied by the height. So that is the equation we are using. So we'll substitute these relationships in this particular equation, and you will get some result. Okay, so Tnx just taking all these terms to the right hand side, so we'll get sigma x into nx into a plus tau xy into ny into a plus tau xz nz into a plus 1/3 s into a multiplied by tau. So this equation are taken Pnx on the left side, all the other terms are taken on the other side. This will become minus. So Ax becomes Nx into A, Ay becomes Ny into A, and Az becomes Nz into A, and the volume becomes as given here. So as you can see here, the A gets cancelled from all the sides. So what you get is Pnx equal to Nx into sigma x plus Ny into tau xy plus Nz into tau xz plus one-third gamma multiplied by h. So that is what equation we are getting. So is it clear till now what we have done? Any questions or any doubts at this point? So we have summed up forces in x direction. We got some area terms, and because of the geometry, there is a relation between that arbitrary plane what you have selected. When it is projected on xyz plane, there is a relation between the main area and its projection on a particular coordinate axis, which is defined in terms of the direction cosine. So that is the relation that we have got. Now, as in all the cases, so here we are talking about solid mechanics where all objects are continuum. So I think 3 batches have completed, except C batch, others know what is continuum. So can somebody tell what is continuum? So that is the assumption that we make in solid mechanics. So C batch students are safe, but I believe there are other than C batch students here. That is called as homogeneity. Yeah, that is correct, partially correct. Can you just specify more correct? The matter is continuous. Assuming the body to be completely free of any defects or any voids or any cracks. So that means you can make the solid smaller and smaller. In real material, if you go to microscale or nanoscale, you will start observing there are holes, or at the molecular level there will be intercrystalline intermolecular gaps. So those effects we are neglecting here. So here what we are saying is this particular tetrahedron will keep on shrinking till it becomes very, very small, infinitesimally small. In real material, when you make it infinitesimally small, there will be, within this tetrahedron, there may be some gaps. So it becomes difficult to predict what will happen at that time. But for real material, but for practical purposes or engineering purposes, this particular assumption that even if you shrink to smallest level, no problem, means the area will keep on shrinking. So what we are assuming here is that we are assuming the volume to be very small. Volume tends to 0, which also means that what will happen to this particular term? So H will also tend to 0, which means that this particular quantity will also tend to 0. So the body force term, although it exists here at finite volume of the tetrahedron, as you start shrinking, the remaining terms, they are quantities related to per area. So they remain as it is. So they will not change, because Pnx is already considering area tending to 0. So this definition already includes area tending to 0, whereas this particular volume tending to 0 will vanish this particular term. So finally you will get your first Cauchy's equation. So that is on arbitrary plane, so that is on n plane, the traction vector in x direction would be given as nx into sigma x plus ny into tau xy plus nz into tau xz. So that is the first Cauchy's equation. So if you know sigma x, sigma tau xy, tau xz, so that is the first row of traction vector, we can calculate what is Pnx for any arbitrary value of nx, ny, nz. So nx, ny, nz are the direction cosines of the arbitrary plane. So they can take any values. As long as you know sigma x, sigma and the other terms, you can calculate Pnx. Similarly, if you sum up the forces in y direction, you will get the second equation, and if you sum up the forces in z direction, you will get the third equation. So that derivation we are not doing here. But you can see easily some pattern here, and you yourself will be able to tell me what should be the value. So I am just repeating the first equation here. So this is nx into sigma x plus ny into tau xy plus nz into tau xz. Just for your reference, I am writing here the stress matrix. So this is your stress matrix. The stress state at a point would be given in this particular term. The first equation you find some relation. So this is r direction, this is z direction, this is k direction, nx direction, ny direction, nz direction. So if you look at this equation, you find some pattern there. So looking at this pattern, you should be able to tell me the remaining two equations. So just guess what could be the other two equations. That will help you to remember sigma y into ny, that's right. Tau yx into nx. So yx or xy. So nx into tau xy. The last term. So what you see here, it is simply you consider here nx, here ny, and here nz. Just multiply this to this, this to this, this to this. You get first equation, second equation, and third equation would be nx into tau xz plus ny into tau yz plus nz into sigma. So these are called as Cauchy's equation. So if you know the stress matrix, you can calculate now the traction vector on any arbitrary plane. So that also proves that this particular three planes or three traction vectors are sufficient to calculate any of the infinite traction vectors. So previous lecture we discussed that at any point in the body you will have infinite number of stress states. So not stress states, but the infinite number of traction vectors. So those infinite traction vectors can be derived from any of the three mutually perpendicular traction vectors. So these three traction vectors, so this is the first x direction traction vector, y direction traction vector, z direction traction vector. So from these three, you can calculate any arbitrarily oriented plane. So that is the importance of this particular plane. In actual engineering design, you will use it to calculate which is the critical plane. So you know that this particular component is pulled in this direction, subjected to torsion, subjected to bending. So it will lead to some three-dimensional straight. So these components can be calculated by using ordinary the axial stress formula, bending stress formula, shear stress, torsion formula. So from that you can obtain on regular XYZ planes what are the stress components, what we did in first assignment. So this matrix can be obtained at a particular point, but because of all these multiple traction vectors, whether the material will fail or not fail, that is what is, as a mechanical engineer, we would like to know. So somebody who is designing this particular pencil would like to know when it is subjected to torsion, bending, axial load, whether it will break or not break. So in order to do that, you have to find out which is the critical plane where the highest amount of stress exists. So that is called as a principal plane, which also got introduced in the previous semester. So here we'll see that, means later on we'll see that using this stress state, we can calculate which is the critical plane. And to determine this critical plane, we'll be using this Cauchy's equation. So that is the utility of what we are doing here. Usually, any arbitrary plane is also useful whenever you are running some kind of joint. So if you have this particular table, and let's say while manufacturing, it was made in two parts, and there were these two sections were joined together by some glue or fevicol was made here, and they are stuck together, and then it is subjected to some kind of load. And that glue has got, adhesive has got some kind of strength. So one would like to know whether that joint, whatever that fevicol joint has been made, will be able to hold the stress at that particular point. So one would like to know along that plane, normal to that plane, or along the plane, that is what is the normal traction component on that plane and what is the shear component on that particular plane. And then you can relate that normal and shear stress to the adhesive strength of the fevicol or the adhesive, and you can determine whether it is safe or not safe. So once you get traction vector on any arbitrary plane, so if you know which plane you are dealing with, you can directly use these equations. Usually these equations in the Cartesian components are not useful. You have to resolve them. So whatever this particular component will give you Tn bar, so that is Tnx I bar plus Tny J bar plus Tnz J bar. So that is the traction vector on this arbitrary plane. This particular component Tn bar, you have to resolve into normal and shear component. So that is, as a designer or as a designer of some machine, you will require not this traction vector, but what is the normal traction vector and what is the shear traction vector. So you have to resolve this component into its normal component and shear component. So how to do that is what we will see now. So at the end of this Cauchy's equation, what we will get is this Tn bar. So you have got that Tn XYZ component of this. What in general mechanical engineers would like to know is not the XYZ components, but whatever plane you have chosen. So that plane may be that adhesive joint that I have just now told, or you may be knowing a principal plane on which you want to calculate the components. So you would like to know what is the normal component and what is the shear component. So you have to resolve this Tn bar into these two components, that is the normal component and the shear component. So that is what we are trying to do. So what you see here, this N bar is normal to the plane. If this is that fevicol joint, this is the plane that we are talking here. And on that plane, using Cauchy's equation, you have calculated this Tn bar. You want to know what is along n direction and what is along perpendicular to that particular direction. So this is called as a normal component, sigma n bar, and this is called tau n bar or the shear component. Now using the vector operations, some of you may know how do you calculate component of this Tn bar along n bar. So anybody remembers? If you have some vector, this is Tn bar and this is n bar, how do you project this vector along this direction? So there is some operation in the vectors which gives you component of one vector along the second direction. So what is it called? Yeah, that's right, somebody said. So that is the dot product. So if you take dot product of Tn bar with n bar, that will give you what is the projection of Tn bar along the sigma n direction. So those of you who have forgotten or don't recollect, so I have given a separate video, especially it was meant for DSY students, but others can see just to refresh this point. So we will get the magnitude of projection of one vector, that is Tn bar along n bar, so that is a normal component. So magnitude is denoted by the double bar. So this indicates sigma n bar is this vector. The size of this vector is denoted by this double bar, so that is given as Tn bar dot n bar. So that is how you will find what is the magnitude of the normal vector. Now written explicitly this. So the magnitude of normal vector. So Tn bar into n bar. So we know that Tn bar is Tnx I bar. So this can be written as Tnx into nx plus T bar into n bar plus Tnz into n. Since Tn bar is Tnx I bar plus Tny z bar plus Tnz k bar, and n is nx I bar, ny j bar plus nz k bar. So the dot product will be I bar terms product, j terms product, k terms product. So that is how we get the magnitude. So we know the magnitude of this vector. So can you write the normal vector in terms of magnitude? So this is the magnitude that we have calculated. So this number comes as 10. The actual vector along n bar direction will be given by magnitude multiplied by n. So this particular number comes as 10. So 10 multiplied by nx I bar plus 10 multiplied by nx j bar. We will take one numerical problem where it will become clear. So this is the entire vector having magnitude this much and oriented around n bar. Now what remains to be known is the shear component. So we have to calculate what is the magnitude of this shear component. So this particular shear component, can somebody think how we can calculate this component? We know that is Tn bar is composed of two components. One is sigma n bar and the remaining is tau n bar. So can you just think how you know Tn bar from Cauchy's equation? You know sigma n bar by this equation. So how one can find out tau n bar? Yeah, resultant vector is a statement which is correct. Who is resultant of what? That's right. So if I want to know Tn bar in the vector form, so Tn bar, this vector is resultant of sigma n bar and tau n bar. So can you write that in the vector form? So Tn bar is resultant of sigma n bar and tau n bar. So in the vector form, how it will look? You have got Tn bar, which is addition of sigma n bar and tau n bar. So how do you write here? So the simple vector addition will be sigma n bar plus tau n bar. We can calculate the shear stress vector as Tn bar minus sigma n bar. So that is how one would calculate the value of the shear stress component. So once you know this particular component, so we already know what is the normal component and what is the shear component. So one can then take the decision whether that plane is critical or not critical, whether the failure will happen there or it will not happen there. So there is a numerical problem based on that, but I don't think we have time to complete that today. So we'll take it in the next class. So any questions or doubt at this point?